How's it going, everyone? Hope everyone's doing alright today. Do you have any questions over section 3.4? The even problems that I assigned? Okay. Alright. The question is, what were the even problems that I assigned? Okay. Anyway. Let's see. This is on page 250. We had those four. First of all, that's just the matching problems with the shape of the graph to the name of the type of graph, the name of the functions. Let's see. Did I assign 19 through 26? Well, I shouldn't have. I should have assigned 11 through 18, and then 27 and 29. Did I mess it up? and 29 on page 250. Square is a cube. Okay. So here, part A, we want f of negative 2. And so as we discussed on Monday, we figure out, okay, if x is negative 2, is it between negative 3 and 1, or is it between 1 and 5? Well, negative 2 is certainly between negative 3 and 1. So we use 2x plus 4 for f of x. And then plug in negative 2. And that gives us a value of 0. B, f of 0. Same approach. We again decide which of these that 0 is part of. 0 is between negative 3 and 1, so we still use 2x plus 4. And now we plug in 0. It gives us a value of 4. Part C, we want f of 1. Okay. 1 is right here. Now, 1 we have to be careful with because it's where it switches from here to here. But whichever one says equal to 1, which is the first one, we'll continue to use that one, 2x plus 4. So f of x is 2x plus 4, and then we plug in the 1. And then part D, if we evaluate f of 3, 3 is certainly between 1 and 5, so we would choose x cubed minus 1. And now sub in the x equals 3, and we get 26. Okay. So the main thing here is making sure we pick the correct place to plug in the values. So it's more just a matter of verifying your answers, August. So on 238, I did 17 through 24. Oh, yes, yes. So let's see the even answers there. So 18 intervals where the function is decreasing. That's from negative 2 to 0. Well, also negative infinity to negative, or sorry, negative 10 to negative 8. negative 2 to 0, and 2 to 5. Number 20. Let's see, is there a local maximum at 5? No. In fact, that's a local minimum at 5. Okay, 22. List the numbers which f has a local minimum. What are the local minimum values? So you have a minimum of negative 4 at x equals negative 8. We have a minimum of 0 at x equals 0. And we have a minimum of 0 at x equals 5. Let's see, 24, the absolute maximum will be 10. F of 2 equals 10. Oh, and 23 also. Find the absolute minimum. Okay. And then 23. Let's see, minimum would be negative 4. Which is f of negative 8. Okay. When we're looking at the absolutes, the absolute minimum, it would be the single lowest point on the graph, and this is vertically the lowest point on the graph. So negative 8 comma negative 4, that's where our minimum is, but specifically negative 4 is the minimum value because that's the y value at that location, and that's the smallest y value on the graph. Okay. Similarly, for number 24, we have a maximum value of 10. That's the highest point on the graph, and it occurs at x equals 2, so we could say the maximum is 10, or maximum value is f of 2 equals 10, something to that effect. But we do want specifically the y value included in that. The x value may or may not need to be included. Okay. Okay. Were there other questions on homework? Okay. All right, today we're gonna cover section 3.5, which wraps up our discussion of chapter 5 or chapter 3. Sorry. And this section is on graphing using transformations. And the idea is that we could start with the f of x equals x squared. That's our basic parabola starting at the origin. Okay. And we can modify that in a consistent way that allows us to account for changes that are vertical and horizontal as far as moving the graph from one place to another. We could stretch the graph, we could compress the graph vertically or horizontally, but we'll just look at vertically. And we could also reflect the graph vertically or horizontally. Probably we'll just look at horizontal reflection. And we'll come back and get we'll look at vertical reflection today, and we'll come back and get horizontal reflection in chapter 5. Anyway, and so this is something that we'll continue to use at various points in the remainder of the course. Anytime we get to graphing, this is one of the main techniques that we like to use. So it does require us to be able to utilize our library of functions that we discussed last time, which it expects us to know these basic shapes that are associated with the different functions. Like x squared looks like this. Absolute value of x has a v shape. What does the square root of x graph look like? That kind of thing. And so we'll basically start from the what we call the basic function, or the original function, and we'll make modifications to that from there. And using this series of modifications, we should take this graph into what the other graph will be. For instance, if we had f of x is negative x minus 2 squared plus 3, that'll look like that. Okay, so that's the kind of thing that we'll build up to, because this one actually has 3 different transformations applied, because it's shifted horizontally, it's shifted vertically, and it's reflected. Okay, reflected means it's flipped over from one direction to another. So, anyway, so that's kind of what we're going to be dealing with in this section. Now, there's multiple types of transformations that we'll look at. So let's begin with the vertical shift, which is probably the easiest of the bunch. And the vertical shift occurs when we add or subtract a number at the end of a function. If the number happens to be added, we move the graph up. And if the number is subtracted, then of course we'll move it down. Okay, so just as a very basic example to start off with, if we have f of x equals x squared minus 3. Well, we have basically the equation as x squared, but after that, at the end, so when we say at the end it's separate from the x squared, we have a minus 3 subtracted. Because it's a value that's subtracted, we know it moves down 3 units. Okay. And so our graph will be, normally x squared starts from the origin, so we go down 3 units from there. Put a point there where our graph now begins, and we draw the same shape. We haven't deformed the shape at all, we've just changed the graph's location on the plane. So we just basically took the whole object and shifted it down 3 units. Okay, and that's what it means when we have a vertical shift is the shape or the the general shape of the curve or the function is identical. We're just shifting where it is in the plane, like we're taking the whole object and moving it up, or the whole object and moving it down. Okay. So if we have, for example, f of x equals the square root of x plus 2, well, this time plus 2 means that we shift the whole graph up 2 units. Okay? And again, square root of x starts from the origin. We go up 2 units from there. And we draw the kind of typical square root of x shape, which is a curve that goes up and over to the right from the starting point. Remember that square root of x is basically the top half of a parabola that points to the right. Okay. So vertical shift is, I think, pretty straightforward, and I hope y'all are seeing that just fine right now. Let's move on to horizontal shift. And the idea with the horizontal shift, of course, it means that we're going to be moving the graph left or right. That's what horizontal means. In this case, or probably the best way to interpret this is this occurs when a number is added or subtracted inside the function. Okay. Now, when we say inside the function, that would be either inside parentheses, or if we have like a square root, it'll be inside the square root. For instance, x plus 3 squared, that would be a shift inside the function. With the absolute value of x minus 1, that would be a shift inside the function. Or a square root of x plus 2. Plus 2 would be a shift inside the function. And so that's what we mean when we say inside the function. It's inside parentheses or inside the kind of the main operator of this expression. Now, again, we have a number added or subtracted. If the number is added, we shift left that many points. And if the number is subtracted, This will shift right, of course. This one is a little bit more counterintuitive. It's basically our shifting is opposite of where we expect it to be. Added we think would be moving to the right, but actually it moves us left in this case. And similarly, subtracted is actually moving us to the right. So this is a shift left, right, and left. Okay. The reason it functions that way is when the number is added or subtracted inside the function, it's affecting the x values rather than the y values. Now, the vertical shift was absolutely affecting the y value since it happened after the main function. So by adding 2 or subtracting 2, it would move it up or down that many places. Because this number is added or subtracted before the main operator takes place, whether it's an expression being squared or the absolute value or square root, for instance. Because of that order of operations, this occurs before that order of operation. That's what makes it a horizontal shift instead. The reason it comes out opposite is it's kind of like how we had with the equation of a circle, where it was if we had x plus 3 squared, then negative 3 was our first part of our center of the circle. It's directly related to that. So basically, when we see x plus 3, the 0 value is actually whatever value of x makes this 0. So if we have x plus 3, we set x plus 3 equal to 0, we get x equals negative 3. That's why it's a shift left of negative 3. Same thing here. If we set x minus 1 equal to 0, we get x equals positive 1, so it's a right shift of 1. X plus 2 equals 0, we get x equals negative 2, so that's a left shift of 2. The other way we can remember that is it's just backwards. Whenever we have a horizontal shift, it's kind of backwards of how we expect it to be. Added would be left, and subtracted would be right. Alright, let's graph a few of those. If we have f of x equals square root of x minus 2, in this case, the minus 2 means we'll shift it to the right 2. So go right 2 from the origin and draw our square root graph from there. Okay. If we have x plus 3 parentheses squared, that is left by 3. So 1, 2, 3 left, and then we draw from this new location just our basic parabola function, or parabola graph. Because the function is still x squared, we just have this extra number in here which tells us we're moving one way or another. In this case, it's to the left. Now, in addition to that, we can actually look at problems where there's two shifts now, vertical and horizontal. So if we say, for instance, f of x equals the absolute value of x minus 1 minus 3. Minus 3 is at the end, separate from the absolute value sign. So this is the vertical shift. It'll be down 3. Minus 1 is inside the absolute value bars, so it's inside the function. And that will be a horizontal shift to the right. So basically we're going to start at the origin. The nice thing about each of these graphs is that they start at the origin. We'll move right 1 and then down 3 from there. So from the origin, right 1, and then down 3. So right 1, down 3. And then we just draw in their normal absolute value graph, which is a V shape, starting at this new location. Okay. All right. So that is our horizontal shift. Vertical and horizontal are pretty straightforward. Most of these are straightforward. It's when we start combining multiple ones together, it starts to get a little bit more confusing. So we have to be very careful we pay attention to which number we're looking at or which aspect. How does that affect the shape of the graph or the location of the graph? And making sure we interpret that correctly. The next transformation we're going to look at is reflection. Now reflection occurs when the graph is, or when the function is multiplied by a negative on the outside. I guess we could say vertical reflection occurs when the function is multiplied by a negative on the outside. Okay. When we mean on the outside, we would say, for instance, f of x equals negative x plus 2 squared. This would be a vertical reflection. Okay. So the fact that we multiply by a negative on the outside reflects it vertically. As you might expect, a negative on the inside reflects it horizontally. I think I'm going to save that one for chapter 6, so we'll kind of ignore it for now. So we'll just focus on the vertical reflection in this section. Yeah, basically it's just that we have an extra minus in front of everything, whether it's in front of the parentheses being squared, or the absolute value, or the square root. Whatever function we're looking at, it'll be right there in front of everything. Okay, and that's how we normally expect to see it. So the overall effect there is that it basically takes the image and takes the top half, which normally these graphs are going to be above the x-axis. It's going to flip them so that we're now facing the opposite way, going down below the x-axis instead. So if we have, as an example, move this down, we have, let's see, f of x equals negative absolute value of x. Okay. The only thing that we have happening there is that we have a negative on the outside. So we know this is going to be our reflect down. And so our graph, in this case, would be the same V shape that we expect with the absolute value function, but now going down instead of up. Okay. give you another second to look at that, sorry. Let's look at another example. This one will combine a few more components. So we have a reflection, we have a horizontal shift, and we have a vertical shift. Which two directions are our shifts taking us here? +2, is that left or right? And +4, is that up or down? Left and up. Yeah, the one at the end, of course, what if it's plus, we know it's up. If it's minus, we know it would be down. This one's the one that makes sense. But the one inside the function is always opposite. So +2 would actually be to the left, minus would be to the right. And then, of course, we have the minus in front, where we reflect the graph down from wherever it ends up. Okay. So left 2 and up 4. So 1, 2 left, 1, 2, 3, 4 up. We'll go ahead and make our mark there, but now because it's reflected down, instead of going up from this point, it goes down instead. Okay. What about the two horizontal and vertical shifts here? Which directions do these go? Right and up. Right 3 and up 1, and of course reflect down. One of the things that you see I'm doing here is that for each of the transformations that are in the problem, underneath them I'm indicating what they do to the graph. Like for the shifts left to right, up or down, I write down an arrow to show which way it's going. And then for the sign in front, I also comment what it's going to do. I would recommend you do that. You don't have to necessarily. At least when you're working out on your own paper before you create the graph, I think it's a nice way to get started. And that way when we go to graph it in the next step, we know which directions we're going from the origin. We're going right 3, up 1, and then we'll just draw the graph going down instead of up. So left 3, up 1, draw the graph going down instead of up. It takes a little bit of practice. It's not too bad in the grand scheme of things, but we do need to make sure we work to get those things straight. I feel like it's not focusing great today. Is it focused? I may just be a little bit asleep still. Anyway, it's probably fine. So that's our first three transformations. The last one that we look at is where the graph is either stretched or compressed vertically. Okay. This occurs when a number is multiplied in front of the function. And for example, we might have 3 times the absolute value of x minus 1, or we could have negative 1/2 times the square root of x minus 2 plus 3. In this case, these two numbers would be either stretching or compressing the graph. Now, I want you to notice right here in particular we have a minus and we have a 1/2. Remember, our minus is doing the reflection that we talked about before, and the 1/2 itself is doing something else. So we actually consider those as two different transformations, the negative and then the 1/2. So we want to be careful we don't try to mix up those concepts. So, A, if we multiply by a number bigger than 1, the graph is stretched. And then B, the graph is compressed if we multiply by a number smaller than 1. So we can see in our two examples I wrote down here, this one is multiplied by a 3, so it's going to be stretched vertically. And this one is multiplied by a 1/2, so it's going to be compressed vertically. Now when we say stretch or compress vertically, we're looking at the graph as it is moving vertically. So stretching it takes a graph and makes it taller than it normally would be, but does not change the width. The net effect of that is actually looks like we shrunk it horizontally, interestingly enough. But it's basically taller and more narrow. Let me write that down. So taller and more narrow. And then if we compress the graph, basically we're squashing it towards the y-axis, squashing it vertically. So when we make everything shorter, it actually ends up looking wider than it would be. So if we took a parabola and we compressed it, it would be more of a bowl shape than a traditional parabola, depending on the ratio of the compression that was taking place. So in this case, it'll appear shorter and wider. Okay. So for example, if we have f of x is equal to 2x squared versus if we have f of x equals 1/2 x squared. Our original x squared graph, we know, it's just a normal parabola starting from the origin. 2x squared okay, it's going to stretch the graph, and then 1/2 x squared will compress the graph. And it might look something like that. Now, you'll notice that if you happen to read the textbook, they're all about plugging in points and having points of reference on this graph. I don't want us to work that hard. The whole intent of this, learning how to graph using transformations, is that it doesn't require a lot of extra work on our part beyond understanding how the transformations affect the graph itself. So we want to be able to recognize that if we multiply by 2, it does stretch the graph. If we multiply by 1/2, it does compress the graph. As far as how we sketch that, though, unless we have like a graphing calculator or software that will graph for us, we don't have to worry about this too much. Just take what we would normally do for the original shape and then exaggerate it in that direction that it's being changed. So if it's being stretched, make it look taller and more narrow than it started out. And if it's being compressed, we'll make it look flatter and wider than it normally would be. Whether this exactly is 1/2 or how does that compare to 1/3, we're not terribly interested in worrying about that here for our purposes, because the goal is to be able to quickly sketch a graph of the function without going into a lot of that detail. And I think the book loses sight of that when they gives us a bunch of extra points that they want us to graph, and making sure we have all these different function values included. It really just slows us down, I think. Anyway, let's look at some examples that include all 4 transformations. Okay, this one would somehow incorporate a lot of extra negative 2's. What are the horizontal and the vertical shifts here do? Which direction is the graph moving based on those 2 things? To the right and down. Now what does our negative 2 in the front do? Reflect and stretch. Yes. So the negative reflect down, and then the 2 stretches the graph, which will make it appear more narrow, yes. Okay. Normally, square root of x looks like this. And so our modified graph, which I'll just call it f of x, where from the origin we go right 2 and down 2. Instead of drawing it up and over, we reflect it, so the whole graph flips down. So now we go down and over. Square root graphs are a little bit more difficult to kind of exaggerate what's happening with them, like whether it's been stretched or compressed. So we just do the best we can with that. Main thing is we got the other 3 correct, and it, at least for stretching, we could say an attempt was made. So. Yeah, this probably wasn't the best graph to demonstrate a stretched or compressed image. So let's look at a quadratic. So in this case, we have 4 different transformations. What do these 4 transformations do? Reflect down, compress, right, and up. Good. Yeah, and again, I encourage you, like when you're working through these problems, to write down, like I'm doing here, what each of these things does to the graph, and then from there we can create the overall picture. On the exam, when we have these questions, these will be ones that certainly you'll have to scan and upload, so you can graph on your own paper, then scan and upload the image. You could use graph paper if you want for that, but it's not required. You can just freehand it like I'm doing here. Again, the idea is that we get a good sketch. We're not trying to look for a perfect graph in this case. If we want a perfect graph, we have technology, and we can just plug in a bunch of values if we're going to do it that way. We're just trying to create a very rough sketch so we know kind of which way the graph is going, where it is on the plane, and what it looks like. We don't have to be perfect to get all those things kind of in our mind. And that's going to be the emphasis here. Is just creating a proper sketch that at least illustrates these 4 transformations, even if it's not in exact detail. I mean, we should be able to get the shifting right, but the other 2 are kind of a little more open-ended as far as what it looks like. Let's see, so we would go right 3, down 2. It's reflected down, so our parabola is going down, but it's also been compressed. So we'll draw it out a little bit wider than we normally would. Again, just to exaggerate the shape. It doesn't have to necessarily be exactly what a 1/2 multiplier would make it look like, but similar. Any questions on these? Okay. So probably on the test I'll go ahead and put like 3 of these as separate questions, and they'll have 2, 3, or 4 transformations on each question. Graded accordingly from that. Just how well you've nailed each of the individual transformations and then putting it together in the graph. So Actually, and that actually wraps up our discussion of this section. Let me switch and we can look at the review for chapter 3. Canvas. Oh, sorry, let me turn on the screen. Let's see. Probably, and this is what I normally do, I'll go grab it from my previous course and upload it to our course. Since I'm not in my office where I have all my files, so. Let's see, probably spring 2020, yeah, that's when I had it. Files. Not as organized here. Test 2 review. Okay. Yeah, test 2 review for chapter 3. So, the first problems is being given a function and plugging in different terms to that. We have a number that we plug in, a variable expression, and then a more complicated variable expression. And so we want to be able to plug those in and evaluate that expression. Okay. Find the domain of the function. We have a rational function that we would like to find the domain of, and I made that a multiple choice question there. And generally, whatever is a multiple choice question on the review will also be a multiple choice question on the test. So you can take that as a guidance. Domain of a radical function, similar setup. Okay. Now for these next problems, I give you a graph, much like we saw in sections 2 and 3. So we want to figure out where the graph is increasing, decreasing, or constant based on this picture. Find its domain and range, and determine if it has an absolute maximum, a local maximum, absolute minimum, and local minimum. So basically, everything that we had talked about before, and that was mainly that was section 2 and section 3. I think. Now, one thing I didn't include here that I may include on the test as well is, what is f of negative 2? We go in and say, okay, f of negative 2 is equal to negative 4 since we have this coordinate on the graph. Okay? Or I might say, when is f of x equal to 6? And that occurs right here in this last coordinate. The y value is 6, so that occurs at x equals 7. So I didn't put those here. I do want to include those on the test, I think. So I may add an additional question here, and it'll just be fill in the blank like these are. Yeah. So be ready for that as well. We have a difference quotient. Find the difference quotient f of x plus h minus f of x divided by h for this function, and you can expect to see a similar function on the exam. It'll be quadratic basically, but there may be some coefficients here or there that we have to worry about. Now this it's a piecewise defined function. The way I've asked this question is a little bit tricky. I think it tests your knowledge a little bit better. That's why I like it expressed this way. So I give you this piecewise function, and then I give you 4 function values. I basically say which one of these is false. So to go through, plug in negative 3, and make sure you plug it into the right piece, and then evaluate it and see if it is equal to negative 10. And if that's true, then we'll go to the 0 and see if that's equal to 1. Repeat for the rest of those. 3 of these will be true. They'll actually give us the right number on the right hand side, and 1 of them will be wrong, and we want to pick out the one that's wrong. The other way I could ask this is I could turn around and say, okay, only one of these is true, which is that. And it'd be a similar process, but we're looking for the one that's different from the others. One false one here, or one true one maybe on the test. I may ask it the same way, I may switch it around, but that's the general concept. Okay, so here's a function, and we want to answer the following questions. Is the coordinate negative 2 comma negative 8 on the graph of, well, that should be an f of x there, I'm sorry about that. And so we know that we can test that by plugging in negative 2 for x, calculating the function value, and seeing if it's equal to negative 8 or not. And then it's basically a yes or no question from there. If f of x is equal to 12, what is x, and then what point or points are on the graph? So basically when we say f of x is equal to 12, that's a value plug in on the left-hand side, and then we move it over to the right and we solve the resulting quadratic equation. And we should have 2 answers there. We'll just make sure we express them properly. Now, it says use the graph of f of x equals x squared to sketch the graph of g of x equals negative x plus 2 squared minus 3. So I've given you the shape of the basic graph here. This is f of x equals x squared. And then I want you to sketch it using these transformations on this other plane, which would be nice if I had a test to hand out to you if we were like sitting in the classroom. But we can't do that right now. So instead, you'll just need to graph that on your own paper, unfortunately. Anyway. Here's another question using transformations. Here we have graph f of x equals square root of x. These 2 transformations. And negative absolute value of x plus 2. And I believe that's it. That's the entire review right there. Let's see, I just have 12 questions here, so it's a little bit shorter than the last one, I believe. And again, like I said, I'll probably go back and add another couple of questions to go with this graph, dealing with function values. What is the value of f of negative 6, or when is f of x equal to positive 6, or something like that. We went over those when we discussed section 6 or 3.2, but I didn't include them on this review, and I really want to. So please make sure you look at those. And what we'll do is on Monday we'll go over this review. And I will make sure I get that uploaded to Canvas as soon as class ends today. Do you have any other questions before we wrap it up? Alright, I don't have any other homework for you. Just the main thing is work on the review. You don't necessarily have to do all of it, because I'm going to work through it in class on Monday. But I do recommend that you go ahead and try it out and see what you can do with it before you start studying, or if you want to go ahead and start studying and work on it some more, or just let that be part of your studying. Whatever approach you want to take, I think it'll be good. as long as we're preparing for the test. That's the main thing. But anyway, we'll leave it at that for today. So you all have a good rest of the day, and yeah, I'll have a good weekend, and I'll see you all again on Monday. Bye.